Okay, so for tutorial 1, thickness of a falling film. Water at 20 degrees Celsius is flowing down a vertical wall with Reynolds number of 10. Calculate A, the flow rate in gallons per hour per foot of wall. Okay, please take note of this. Per foot of wall width, and the film thickness in inches. Okay, so you are given the Reynolds number here and the film thickness formula over here. Now we need to understand what is the viscosity and the kinematic viscosity of water at 20 degrees Celsius. So over here we can refer to the table given in here. Okay, so take note that at 20 degrees Celsius, this is the viscosity and kinematic viscosity of water. So how are we going to approach this problem? So you are given the Reynolds number over here. So we want to find the flow rate per foot width. Okay, so the flow rate is given by W is the mass flow rate divided by the density and the width. Okay, we arrange this, okay, and we get this. So we know that we can get the viscosity, the kinematic viscosity over here, and substitute the value in. We were given the Reynolds number of 10. Okay, so that is how we can easily solve for the flow rate. Then we will do unit conversion because it wants it to be in gallon. Okay, and we basically just do unit conversion, which is, so 1 gallon is 3,785.41 centimeter cube. Okay, therefore we can easily cancel this off. Okay, now 1 feet is 30.48 cm. Okay, that means we can take this off. And 1 hour is 3,600 seconds. Okay, so seconds, and we will be left with this value. Okay, so for part B, we were given the film thickness formula over here. Okay, so the kinematic viscosity is equal to the viscosity divided by the density. Okay, right here. Therefore, notice that you have rho over here, so this viscosity divided by 1 of the rho, the density. Okay, change it to the kinematic viscosity over here, right? Therefore, we can split this equation into these two parts, which is the mass flow rate, density, and the width, which is here. And because we have calculated the flow rate over here, which is this, right? Okay, so we can write the equation into this. Substitute the values in, so 3 multiplied by the kinematic viscosity divided by G, okay, times cos theta, okay, cos beta, sorry. So beta, because this one is of a falling film, so meaning to say this is your wall and the water flows down vertical like that. Therefore, the degree of angle over here should be 0 degree. That's why we substitute 0 over here and substitute the value for this, which we have already found in part A. Substitute it in and perform your calculation and convert it to the required unit, which is in inches. Okay, multiply by 1 inch divided by 2.54 centimeter. This unit can be cancel off, and we will be left with 3.60924 times 10 to the power of negative 3 inch. Okay, so for the second problem, determine the capillary radius by flow measurement. So one method for determining the radius of a capillary tube is by measuring the rate of flow of a Newtonian liquid through the tube. Find the radius of a capillary from the following data. Okay, so we are given this data. So the length of the capillary tube, this is L. Kinematic viscosity of fluid, this is V. Density of the liquid, rho. Pressure drop in the horizontal tube, delta P. Okay, and mass rate of flow through the tube is small letter W. Okay, so we are given this equation and the Reynolds equation here, so we need to determine the R. Therefore, okay, so we are given this, so we rearrange the R. Okay, and notice that, remember, V is equals to mu over rho. Okay, so the kinematic viscosity is the viscosity divided by the density. That's why over here we can take the density out, because we are not given the value of the density, so it is better if we change it to the kinematic viscosity instead. Then we will end up with this equation. Okay, then take out the R, rearrange, okay, and substitute your values in. So 8 multiplied by the kinematic viscosity of the liquid which was given, the mass flow rate through the tube which was given, the length of the tube, and then we have to convert this to meter because everything here is in meter, divided by pi, and the pressure drop, which is delta P. Okay, and then we have to convert Pascal. Okay, so over here we can now start cancelling the units. So you have second here, second. Okay, make sure that the units are correctly cancelled off. Okay, kg here, and you are left with meter, okay, over here as so. Alright, so by the end of the day we will get this value. Okay, so because it is the root of 4, so the meter here, after it divides, it will be meter. Okay, and then convert this back to cm, we shall get this value over here. Then we should check if the flow is really laminar using the Reynolds formula which was given in the question. Okay, so substitute the values in, so 2 over pi multiplied by mass flow rate, the R, the radius, which is here, that was found, the kinematic viscosity, and the density. Okay, then we will get 65.972. So it is about 66. So for laminar flow, the Reynolds number should be less than 2100. Since it is 66, therefore this is confirmed a laminar flow. So for the third problem, volume flow rate through an annulus. A horizontal annulus of 27 feet in length has an inner radius of 0.495 inch and an outer radius of 1.1 inch. A 60% aqueous solution of sucrose is to be pumped through the annulus at 20 degrees Celsius. At this temperature, the solution density is 80.3 pound per feet cube, and the viscosity is 136.8 pound per feet hour. What is the volume flow rate when the impressed pressure difference is 5.39 psi. Okay, so we are given a set of numbers here, so we have to identify what is what. So length here is denoted by L, capital L. The inner radius is denoted by small letter r. Alright, then we also have the density rho over here, and the volume flow rate, which is the mass flow rate divided by the density rho, and the pressure difference is PO minus PL. Okay, so we are given this equation. Okay, so then how are we going to approach this problem is, so we are given this equation. So since we want to determine the volume flow rate, we have to divide. Okay, so we rearrange and take this rho and divide it over here. Then we have this set of equation. So K is actually the ratio of the inner radius over the outer radius. So an annulus looks like this. Okay, it has an inner radius. This is your inner radius, and this is your outer radius. Okay, your inner radius and your outer radius. So your length is 27 feet. Your viscosity is this, which was given, and then we change it to per second. The pressure difference is in psi, so we will change the unit to pound per feet second square. Okay, and the outer radius, which is in inch, we will convert it to feet. Okay, so we substitute the values in. So like here, pi multiplied by the pressure difference here, multiplied by the outer radius, which we have found and converted to feet, to the power of 4, divide by 8, multiply by the viscosity and the length. Then over here we have the ratio here, K. Okay, substitute the values in, and we get 0.10968 feet cubed per second. Then we will check if the flow is laminar by using the Reynolds number. Okay, so in the question we were given that W equals to pi r square 1 minus k square multiplied by rho multiplied by the velocity. Okay, therefore we can substitute W in and rearrange the equation as such. Okay, substitute the values in, and we will get about 1110, which is less than 2100, meaning that the flow is a laminar flow.